My name is Mohammad Reza Moini and welcome to Run Modelix channel. In this video I want to talk about UGENS Fortran subroutine. So I want to show you how you can compile a Fortran UGENS subroutine in Abaqus and how you can develop your own subroutine. So first of all, you need to make sure that Abaqus is working well with Fortran compiler. So you need to make sure that both of them are linking together correctly. And then you need to read more about UGENS or VUGENS Fortran subroutine. UGENS is for static simulation and VUGENS is for Abaqus explicit dynamic simulation. But you need to know all the input variables that go to these two Fortran functions, and you need to know what is the physical meaning of these input variables before starting to write your own subroutine. And then you can write a simple Fortran code for Elastic Shell. So I suggest you to start with just one element and with elastic material to prepare a simple example for your own application, and then you can develop your own code. After that, you need to prepare your .imp file for your FE model. So when you generate your FE model, you can generate a job in the job section of the Abaqus, and you can generate .imp file, and you need to modify that. And you need to compile that .imp file with the Fortran code, with your Fortran code. Of course, you can get the result, and at this time you need to debug your code. So maybe you have some syntax error in Fortran, or you have some bugs in your code, and you need to correct them. And to do that, you need to verify the final results. So because it is a simple shell elastic for the elastic material, so you know the final answer, you know the resultant for force resultants, or you know the final strain, so you can easily verify the final answer, and then you can debug your code. And after that, you can develop your code for more complex problem, for instance, for nonlinear material, or for nonlinear shape function of the shell, or any kind of more complex problems. And then again, you need to verify your final results based on literature or the previous solution of the more complex problem. So this is a subroutine interface. In this subroutine, we have three groups of input variables. In fact, in any kind of subroutine, we have three main groups of variables. The first group is those variables that we need to compute them. So we need to define them in our subroutine. So we need to write a function or some commands, or we need to develop the code to compute these variables. So for instance, here is ddnd, which is the gradient of force resultants with respect to the strain, and force, which includes the force resultants and moment resultants, and state v, sse, and spd. So generally, you have to define these two first variable, but maybe you don't need them. And there is also optional variable pnewdt, so it is an optional variable, so you can modify that and update that or no. And the other variables are passing just for your own information. So you can use these information to compute these variables. For instance, codes represent the coordinate of the integration of the nodes, and KINC represents the increment number, or K step represent a step number, or curve represent the curvature of the shell, thick represents the thickness of the shell, and other parameters. time and temperature. TMP is the temperature, dTMP is a derivative of the temperature in each time increment. So you have all this information, and you can compute the force or the gradient of the force with respect to the strain based on this information. Include abaprom.inc is the library, and in this line we have the dimensions of our input variables. For instance, quartz has 3 components which represents x, y, and z. And in this line, you need to compute, and you need to develop your code and then return end. This is the end of the subroutine. So this is a simple example that I prepared to show you that you can simply debug and maybe start your code. So this is just one element with 4 nodes, so it's S4R element. So the node number is 1, 2, 3, and 4, and we have a 1 integration point at the center, and we can apply a displacement at 2 right point nodes with a displacement of 1, and we can fix the 2 left nodes, so the dimension of the element is also 1 and 1, and then we can verify our code. So we go to Abaqus now. So in Abaqus, in the part I prepared a shell planner. So here we have dimension of 1 and 1. So it's the very simple geometry. And then in property, I prepared the mat number 1, which is a dummy material with a Young's modulus of 200 gigapascal and Poisson ratio of 0.3. It's for a steel, but I just prepared to have a material in the in my .imp file when I want to generate the .imp file. But it's a dummy material, and we will modify it in the .imp material, in the .imp file. In assembly, so it's a simple assembly. In step, it's a static step general, so not NLGeom, it's off. It's a very simple model. In the field output manager, just pay attention, we need SDV. What is SDV? SDV is solution dependent state variables. We need to have this one in order to save the variable at the end of the increment in our Fortran subroutine. I will explain to you where we use this in our Fortran subroutine. And I wrote ERF, the strain, the reaction force, the stress, and SDV, and U, the displacement. So it is very simple for the field output, and for interaction, we don't have any interaction. For load, I have node number 1, number 2, number 3, number 4, and these 2 nodes are fixed, and in these 2 nodes we have a displacement of 1. So in the first step is we need to node number 1 is fixed, node number 4 is also fixed, node number 2 the displacement is equal to 1, and node number 3 the displacement is equal to 1. So it is exactly like the configuration that I show you in our simple example. So this is for loading. For mesh, so we have just one element. So this is my one element. So the approximate global size is equal to 1. We have just 4 nodes here and 1 integration point at the center. And the element is S4R, a 4 nodes shell element, a linear one. And then in optimization, we don't have any optimization. In job, I have 2 jobs here. So first of all, I have no UGENS job. So one element test 101, but don't worry, I didn't provide 100 jobs for this simulation. So it's just the name. So in no UGENS one element, I will create the .imp file. So when you submit the job, you will have a .imp file in your own directory. So normally it is in drive C in the temp folder. So and if you also write input, you will also have the .imp file. So in my case, this is my .imp file, no UGENS one element, and the .imp file includes all the information of the FE model in a text file, so in .imp file. So here, for instance, this is the information of related to job. This is the nodes number and the element. So we have one element that is connected to nodes number 1, 2, 3, 4, and the element type is S4R. The material, it's mat1. This is the layup that I put in the material just to have a layup, and this is the set of nodes. This is the material, material 1. This is the material of the steel that I just wrote it to have a one material here, and this is the static step, and this is the output that I wrote in my step section, strain, stress, sdv. So this is my .imp file when I just create a job file. So I put it into another view. So here I have, here this is for .imp file. So I have the composite layup here. So this is what I have in when there is no UGENS subroutine. So I need to replace this with this information, this one. So what is this information? So here, when we have two stars, it means that we have comments in .imp file. So here I wrote inserting the VUGENS or UGENS. So let me correct this for UGENS. And here we need to have this shell general section. So you can see the difference. So here we have shell section. Here for UGENS we have shell general section. L set, the nodes set is for composite layup. This is for user, so it means that we use user defined shell element, and the properties is equal to 1 and the variables is equal to 1. What does it mean? It means that we write one property in our .imp file, which is 1000 here, and at the end of the simulation, we can save one variables. So we can save one SDV. So remember that the SDV that I told you. So here we have just one state variables here. And one is for the shell thickness. So the first number is the thickness of the layer. So our shell thickness is equal to 1. And this is the input parameter that I will need it in my Fortran subroutine. And transfer shear stiffness is equal to 1, 1, and 0. So in the width one element test 101, we have this in we replace this in with our composite section. So let's go to the Fortran subroutine. But yeah, here. So this is the Fortran subroutine that I created. It's a very simple Fortran subroutine of UGENS. So again, as I said, this is the interface of the Fortran. These are the input variables. This is the library. This is the dimensions of the input variables. And here I wrote variable declaration. So it means that in any Fortran subroutine, you need to declare all the variables that you want to use or you want to define in your Fortran. So for instance, here I wrote Cij, which is tensile and bending stiffness, and Cij is equal to props number 1. Props number 1 comes from the input let me put the .imp file here. So CIJ, so props number 1 is 1000. Why? Because I have just one input variable in my .imp file, one property, and it goes to Fortran to this line. I will save it in CIJ. And for CIJ, I need to declare it as a real number. So if it was tensor or a matrix, I needed to define like this, with higher dimensions. So here I wrote get the parameters. So you can write the parameters here, and then we need to compute the force resultants and its derivative. It means that force and dd and dde. So first of all, you need to make these vectors equal to 0. So in order to avoid any numerical issue, I wrote force equal for all the components of the 4, which is equal to 1 to n sec v. So you can see what is n sec v in the help of UGENS, and all of them is equal to 0 first. So we have normally 6 components of force, 3 components for n11, n22, and n12 for force resultants, and 3 components for moments, m11, m22, and m12. And dd and de is the gradient of the force component of the force vector with respect to the strain. So we have a 6 and 6 matrix. So for all of them I put equal to 0. And then to compute dd and de, I wrote all the diagonal components equal to Cij, and to compute the force, I computed by Cij multiply by the strain. So it's a very simple case, strain plus the derivative of the strain. So it means that we have a simple case of linear elastic material. And in the next step, we can store the results in our state variable. So here in .imp, I requested one variable to save my parameters. So here in for the first SDV, I stored the first component of force, which is n11. And here I can print what I need to know in the .log file. So if you see the .log file, you can see the components. For instance, I printed chords, shape of dnDDE, and epsilon 11. So for instance, we don't have these variables, but I printed these variables in and I can see it in the .log file. So if I go to Abaqus, so this is the result of no UGENS. So when we have a still material, it's for a still material, so there is no subroutine here. But here, for with UGENS, we have the result of the subroutine. So we have one SDV here. SDV is equal to 1000. And as I said, SDV in our case is equal to first component of the force. So here, because it is a linearly elastic material, and I wrote the elastic coefficient as 1000, and I applied the displacement of equal to 1, so the force resultants is equal to 1000, and we have just one element. So now it is working well for my element. So now the result is the Fortran compiler is working well, so the compiler is working well, and we can have the SDV, so we don't have any strain here, because we directly compute the force resultants here. So this is just want to show you the .log file. Maybe I can show you here. So in the .log file, so if you remember, I printed chords. So here chords is equal to 0.5, 0.5 and 0. This represents the coordinate of the integration point, which is at the center of the element. So this is the chord. The shape of DD&D, as I said, is 6 and 6. Why? Because we have force components of 6 components. The dimension of the force is equal to 6, and also the dimension of the strain is equal to 6, and the derivative of the force with respect to the strain will be a second order tensor, and we have a 6 and 6 matrix. And the epsilon is equal to none, because I didn't define the epsilon 1, so is equal to none. The nsec v, as I said, it was equal to 6 for the force, and the d strain is the strain increment that you see is in all increment is equal to 0.1 at the end. So you can simply debug your code by printing at the in your Fortran subroutine to make sure that the dimensions is correct, or you are computing correctly your parameters in each time increment. So I hope it was good. It was helpful for you, and in next videos we will talk about more complex Fortran subroutine.